In this video, we continue our discussion on sequences, and I wanted to do a couple more examples writing sequences as formulas and also as recurrence relations. So let's work with that sequence we worked with in the last video that we wrote as a recurrence relation, and let's try to write it as an explicit formula. So write this sequence as an explicit formula in terms of n. Right. So, oops, I have a little typo right here. Also remember, this is just to refresh an arithmetic sequence, right? Since you add 4 each time to get the next term. To get the next term. Okay. So we said that in the last video, what we did was that as a recurrence relation, we said we just need to say that the first term is 3, and as a recurrence relation, we said that all we need to specify is that the first term is 3, and then the nth term, you take the term before that and you add 4 to it, and that's how you get every other term except for the first term. So now, right, we have to figure out how to write this as a formula or as a function. So I would say, so as a function, I always, whenever I'm trying to figure out how to write it as a recurrence relation or as a function, I like to list out my first few terms and try to notice any patterns. Right, so I know A1 is 3, I know A2 is 3 plus 4, and I know to get A3, I add on another 4, and then to get A4, I add on another 4, right? So each time we're adding on another 4, right? So I have to figure out what's changing each time and how does that relate to the n value, the index, right? So then when I start looking, I notice, okay, the index is 2. Right, when the index is 1, I have 0 4s. When the index is 2, I have 1 4. When the index is 3, I have 2 4s. When the index is 4, I have 3 4s. When the index is 5, I have 4 4s. So when I notice the index corresponds to 1 less than the number of 4s I'm adding together to get the term, right? So that's going to be the key pattern that I use to write my formula, right? So here, n, right, in this one, you have to notice that n minus 1 is 0, right? For 1 minus 1. And then here, n minus 1 is 1. And then n minus 1 is 2. So basically we have n minus 1 4s, right? Because we said whatever index we're on, we have 1 less than that. So we say that to get the nth term, right, we take 3 and we add on n minus 1 4s. And then we can simplify this, right? So we distribute the 4, and this becomes an is 3 plus 4n minus 4. So an is 4n, and 3 minus 4 is minus 1. And that's how we get our formula. So basically, just like we did in the last one, you have to see what's the relationship between the index and the term you're on. And let's do one more. So let's work now with geometric sequences. So remember that we said for geometric sequence, you multiply by the same constant each time. Okay, so let's work with the example we had. Actually, we never saw this example. So let's say we're given the sequence 2, negative 2/3, 2/9, negative 2 over 27, 2 over 81, and so on and so forth. So, like I said, I always like to write this as a list with the term notation for it. So that way I can start to see the pattern between the terms and any pattern between the index and the term that we're on. Okay. So if you notice, for us to go from 2 to negative 2/3, right, what did I do? I had to multiply by negative 1/3, right? And then if I notice again, to go from negative 2/3 to positive 2/9, right, the numerator stayed the same, so that was obviously multiplied by 1, but the denominator was multiplied by 3, right? And the sign also changed. So each time to go from one term to the next, I'm multiplying by negative 1/3. So that would mean that our ratio we would expect to be negative 1/3, because that's the thing we're multiplying by each time to get the next term. So these are easy to write as a recurrence relation, because we can literally see as a recurrence relation, all we have to do is say that we want to start with A1 is 2, and then every other term we're going to take the term before, right, and we're going to multiply that by negative 1/3. So don't let the notation trip you up, right? N could be any number, right? So I know that the term right before n is going to be the n minus 1 term. For example, if I'm saying n is 5, 5 minus 1 is 4, I know that's the term before. So, and I know I take this term and I multiply it by 1/3 to get the next term. So that's how you have to think about the recurrence relations. And then as a function, it's going to be a little bit more difficult. So again, let's write out our terms just because I don't want to keep scrolling back and forth. So A1 is 2, A2 is negative 1/3 times, is negative 2/3, A3 is 2/9, A4 is negative 2 over 27, and A5 was 2 over 81, and we stopped there, right? It keeps going, but we hope we can determine the patterns with at least the first 5 terms. So, right, if you remember in the last one, what we did to try to figure out the function, how to write it as a function, up here was that we decomposed what was going on each time, right? So each time we added by 4. So now we want to decompose us multiplying by this negative 1/3 each time. So let's write the number out as, right, this number we know is 2 times negative 1/3, right? This number we know is the number before, which is negative 2/3 times negative 1/3, right? But we know that the number before we got from this here, separate the 2 times the 1/3. So this becomes 2 times negative 1/3 times negative 1/3, right? And then, right, we're going to take the term before, which was the 2/9, and we multiply it by negative 1/3, right? But again, we said 2/9 was equal to this right here. So we could further decompose this as 2. Let's bring this down into here. 2 times negative 1/3 times negative 1/3, and then now we multiplied by one more negative 1/3, right? So again, I'm taking this decomposed form of the term before of A4. So that's 2 times negative 1/3, negative 1/3, negative 1/3, and then I'm going to multiply by one more negative 1/3. So now let's see, is there any relationship between the index and the term? Well, right here we see we have, right, in this term we have in this term we have 1 negative 1/3. In this term we have 2 negative 1/3. In this term we have 3 negative 1/3. In this term we have 4 negative 1/3. So again, we see, right, in this term we have 0 negative 1/3, right? So we see that the index we're on, there's always one less negative 1/3 accounted for. So if we're calling the index n, then there's always n minus 1 negative 1/3. So that's how we're going to write our function, right? We'll say that an is going to be 2 times n minus, well, we're not multiplying n minus 1 times negative 1/3, right? That's how many negative 1/3s we have, how many. So notice that, right, this is negative 1/3 squared, which is different from 2 times negative 1/3, right? That's not what we're doing. And then this is negative 1/3 cubed, and this here is negative 1/3 to the 4th. So actually n minus 1 is the power of negative 1/3, right? Because this time we're multiplying. So this is negative 1/3 to the n minus 1. The n minus 1 power. And that's our function. So really, like, to do these things, you really have to determine patterns and relationships and try to decompose things as much as possible to help you connect the dots more clearly. So now let's talk about the limit, okay, of a sequence. Right, so it makes sense to discuss the limit of the terms of a sequence as n goes to infinity, right? So what does that mean, right? Basically, we're saying if we have a sequence, let's use the proper notation, an, that's equals to a1, comma a2, comma a3, dot, 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 comma an, comma, dot, 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 all the way to a million, right? Like, what's going on all the way down here? We want to know what's going to the terms, right? So we want to see, do the terms keep getting bigger and bigger and bigger, right? Do the terms keep getting smaller and smaller and smaller? right? Like, we want to see, like, are they changing signs? So do the terms stay positive? Do they change sign? Right, and do the terms get closer and closer to one specific number? So this is kind of like what we want to figure out, and that's what the limit, these questions are what the limit is going to figure out for us, the limit of a sequence. So let's just define a convergent and a divergent sequence to begin with. So given a sequence an, if the terms an become arbitrarily close to a finite number, right? So that would be the last question we ask. Are they getting close to a specific number? A finite number L, as n becomes large, then we say that an, right, if we take a limit and we get a real number, a finite number, we say that is a convergent sequence, right? When something approaches a finite number, we always say it converges. And L, right, the number it's getting closer to, is the limit of the sequence. So here, right, we're basically saying that the limit as n approaches infinity of an is equal to some constant L. And then if instead a sequence is not convergent, right, so that is, it does not approach a finite number. So instead, right, it either approaches positive or negative infinity, or it oscillates forever. So those are like the two ways that you're not going to approach a specific number. Then we say it is a divergent sequence. So our new vocab words are convergent sequence and divergent sequence. And the definition follows from the definition of whether an improper integral converged or diverged, right? So basically, right, like let's look at this technical formulation, this epsilon definition of convergent sequence. And if this doesn't make sense, you don't trip up on it too much, but I'll try to make it make sense to the best of my ability. So let's say a sequence an converges to a real number L if for all epsilon greater than 0, and epsilon is just a Greek letter, it just represents some number, there, some very small number. That's what we always use it for in math, is to represent a very small number, right, close to 0. Close to 0. So this is just a side note on epsilon. If there exists, okay, so a sequence an converges to a real number L if for all epsilon greater than 0, there exists an integer n such that the absolute value of the term you're on minus the limit is less than epsilon if you're at a specific term. Right, so basically, what is this saying? Right, basically it's saying if you, like, right, we have our sequence A1, A2, A3, dot, dot, dot. We have A capital N plus 1, A capital N plus 2, whatever capital N is, and then we keep going. Basically, we're saying once I reach this point here in my sequence, all of these points, the difference between them is less than epsilon, right? And it's specifically the difference between them and the limit. So basically it's saying, like, there's going to be a certain point where I'm close to the constant L that I'm approaching. Okay, that'll make more sense when I do a concrete example, I promise. All right, so, okay. So the number, so this is basically just telling us, like, if our sequence is going to converge, right? Let's say our sequence converges, like, to 4, right? Then that means that, like, let's just say these are all the terms in my sequence, dot, dot, dot. And we're just going to keep on going. And then we're going to reach a point where maybe, like, we're at 5. And then we're at, like, 4.5. And then we're, like, at 4.25. And then we're at, like, 4.1. And then we're at, like, right? So, like, as we get closer and closer, there's going to be a point where the difference between the term that we're on, the A capital N that we're on, and 4 is basically going to be almost 0. So that's less than epsilon, which epsilon, because remember, epsilon is like some number like 0.0000001 or something like that, right? So that's what this definition is trying to explain. So the number L is the limit of the sequence, and we already know that we write that the notation for this is the limit as n approaches infinity of an is L, or equivalent, we could also just simplify it and write it an approaches L, right? And this, again, is the same definition of a convergent sequence. This is just like the technical math, the more technically mathematical definition of a convergent sequence. And then again, if the sequence does not approach a finite number, right, then we say that it is a divergent sequence. Okay. And let's do an example to hopefully pull this all together. So let's look at this example here. The terms, let's say we were given the sequence 1 minus 1/2 to the n. Right, so A1 is going to be 1 minus 1/2 to the 1, which is just 1 minus 1/2, which is just 1/2. And then A2 is going to be 1 minus 1/2 squared, which 1/2 squared is 1/4, so then we're left with 3/4. And then A3 is going to be 1 minus 1/2 cubed, which is 1 minus 1/8, so that means we're left with 7/8. And then A4 is 1 minus 1/2 to the 4 is 1 minus 1/16, so that means we're left with 15/16. And then A5, right, is 1 minus 1/2 to the 5th, which is 1 minus 1/32. So that's 31/32. So as you can see, the further that we go down this list, right, if I keep on raising 1/2 to, like, bigger and bigger powers, right, like, let's ask Google what 1/2 to the 100th power is, right, so 1/2 to the 100th power is approximately 7.88 times 10 to the negative 31, right, in scientific notation. So this is really like 0.000000000, right? There's like 30 zeros, and then there's 788. So it's basically, what I was trying to show is that as the n gets bigger, the value of 1/2 to the n gets closer and closer and closer to 0. So that's the key point, is that as we go down, as the n becomes bigger, this becomes smaller towards 0. So then what's left is just going to be this 1 right here. And we see that happening right here, right? Where 1/2 isn't that close to 1, right? But then when we go to 31/32, now we're, right, what's 31/32 in decimal form? Let's see, 31 divided by 32 is 0.968. So we're almost at 1, right? What's 15/16? Right, that's 0.93. We know that 3/4 is 0.75. This is 0.5. And then 7/8, we know that 7/8 is 0.875. So as you see, the decimals, as n gets bigger, are getting closer and closer to 1. So the terms become close to 1 as n becomes very large. And that is indeed our limit. So what we say is that 1 minus 1/2 to the n is a convergent sequence, and its limit, its limit is 1. Right, and let's look at another example. So basically we'll say the limit as n approaches infinity of 1 minus 1/2 to the n, right, is 1. So let's do another one. And let's say we were given 1 plus 3n. Right, so a1 we see is 1 plus 3 times 1 is 4. A2 is 1 plus 3 times 2 is 7. A3 is 1 plus 3 times 3 is 10. A4 is 1 plus 3 times 4 is 13. A5 is 1 plus 3 times 5 is 16. And then if we go down, let's say we do A of 100. A100 is 1 plus 3 times 100 is 301. Right, so I see, right, if I'm at 10,000, right, 1 plus 3, the 10,000th term, right, is 30,001. Right, so I see that as I go down my sequence, my terms are getting huge, right? As I go further down the sequence, my terms are getting bigger and bigger and bigger. So these are not approaching a finite number. So the terms in the sequence 1 plus 3n are getting large as n becomes large. Right, so they are not, right, the terms are not approaching a finite number, right? Because it's just, if I was to plug in 1,000,000 in here, let's see, 3, then I would get 1 plus 3 times 1,000,000, which would be 3,000,001. So it's just going to become huge and huge and huge. So the terms are not approaching a finite number, right? These are obviously going off to infinity because it's just going to keep getting bigger and bigger. If it's a billion, a trillion, terms are not approaching a finite number. So the limit of, as n approaches infinity, of 1 plus 3n, that's actually infinity. And so this sequence here is a divergent sequence. Okay. So one thing that's interesting for geometric sequences, so one key fact, right? If we have, this is specifically only for geometric sequences, so a geometric sequence, so basically if it converges or not, it's going to depend on the value of the ratio r. A geometric sequence with ratio r satisfying that absolute value of r is less than 1 converges to 0. And then if r is equal to 1, the sequence converges to whatever the starting value, right, or whatever the first term is. And otherwise, if the r is anything other than that, so if the absolute value of r is greater than 1, the sequence diverges, which makes sense, right? Because if we're multiplying by something that's going to make our function get bigger and bigger each time, like here, then we know we're going to go to infinity, right? So in a nutshell, if the absolute value of r is less than or equal to 1, then geometric sequence converges. So let's look back at our example to see what's going on, right? So where was our geometric sequence that we were looking at? Okay, here. Right here, we had a geometric sequence where the ratio was -1/3. So we don't even have to do much to see does it converge or not. In this example, since the absolute value of -1/3, which is 1/3, is less than 1, we know that this sequence converges. Okay. And lastly, to end the video, right, I just want to connect the dots between the sequence and the formula that we write, or when we define it by a function, right, a formula of a function of n. So the limit of a sequence defined by a function. So basically, if you're given a sequence an such that we were able to write that sequence as a function of n, like we've been doing for all n greater than or equal to 1, if there exists a real number L such that the limit as x approaches infinity of f of x is L, then an converges and the limit as n approaches infinity of an is L. So basically this is telling us we can just use limits, right, if we have a function for our sequence. And lastly, just for a review, I just want to go over some limit laws and just change them to apply to sequences. So given sequences, so this is still the same limit concept that you learned in calculus 1. and any number C, so C is a constant, if there exist numbers capital A and capital B such that capital A is the limit as n approaches infinity of the sequence an, and capital B is the limit of bn, and the limit as n approaches infinity of bn is b, then, right, we have the same limit laws. Remember, we said that if we take the limit of just the constant, right, that's not changing at all, so it's just going to be a constant itself. If you have the limit of some constant times your sequence or your formula or your function, right, you can pull out that constant out of the limit, and, right, whatever the limit of an is, you just multiply c times that. And then if you have the sum or the difference of two sequences that converge, then the limit is just going to be, right, we can separate out the limit over addition or subtraction, right, either one, and then we just add or subtract the limit values. And then the same thing happens with multiplication, right? If you have the product of two sequences or the product of two functions, you can just do the limits separately, and then the answer is going to be the product of the two limits. And the same thing for when you have the ratio, right, or a fraction of two sequences, right, or equivalently two functions an, you can do the limit of the numerator, the limit of the denominator, and that's just going to be the ratio of the limit of the two things, right? And here obviously we cannot have that the limit of bn is 0, right? So none of the terms could be 0 because that's going to give us a problem in the denominator. And that is just about everything I wanted to cover. Thank you.